Find the shortest distance from the point 2, 1, negative 1 to the plane x plus y minus z is equal to 1. In order to minimize this distance, let's hold space for the x,y,z ordered triple that is the closest one to our point. And what we're asked to find is this minimum distance. So let's recall that the distance formula between two ordered triples in 3D is very much like the distance formula in 2 dimensions, except for we add on this z2 minus z1 binomial. So the distance between our two ordered triples is going to be the x-coordinate of the point on the plane minus the x-coordinate of our ordered triple plus the y-coordinate of the point on the plane minus the y-coordinate of our ordered triple plus the z-coordinate of our point on the plane minus the z-coordinate of the ordered triple, which will be z plus 1 quantity squared. In order to minimize this distance, we need it to be a function of only 2 variables. Our process of using the critical points and then the second derivative test requires a 3D function, 2 independent variables, 1 dependent variable, and where we currently are is 3 independent variables and a dependent variable. So we're going to use the fact that our ordered triple is on this plane in order to eliminate the variable z. We're going to solve for z, which is going to give us x plus y minus 1, and then use this as a substitution in our distance equation down here. So now this d is actually d for distance, right? The distance formula is going to be the square root of x minus 2 squared plus y minus 1 squared plus, we're going to substitute in for the z, x plus y minus 1, and then plus 1, and then quantity squared. And of course, these 2 1s cancel out. So in order to minimize this distance, we would first need to find the first partial, set them equal to 0, get our critical points, and then plug them into the second derivative test. But with this radical, that's going to be quite a process. So notice we're going to get the smallest distance when the radicand is as small as possible. And of course, this is the radicand. So we can use this fact to minimize the radicand and make all of our computations a lot easier. I'm also going to let that radicand be equal to a function, we'll call it f, instead of d. We are going to be using the second derivative test eventually, and so having 2 variables both with a d can get confusing. So we're going to let fxy be equal to that radicand, and that's going to help us stay organized. So to minimize this radicand, we need to find the first partial with respect to x and first partial with respect to y in order to get those critical values. First partial with respect to x is going to be 2 times x minus 2. This derivative is going to go to 0 plus 2 times x plus y. First partial with respect to y, this derivative goes to 0 and we'll end up with 2 times y minus 1 plus 2 times x plus y again. Let's distribute and combine like terms. To get the first partial with respect to x is 4x plus 2y minus 4. And again, distribute and combine like terms here to get 2x plus 4y minus 2. Now we'll set each of these equal to 0 and find the xy ordered pair that makes both 0, which basically means to solve this system of equations. And let's use elimination to get negative 6y is equal to 0 and y is equal to 0. We can take that back to either one of these equations and see that if y is equal to 0, x is going to need to be 1. So the critical point is the ordered pair 1, 0. So now let's recall that in order to determine whether or not our critical point is a max or a min, hopefully it's a min because it's the only critical point we obtained. Let's just double check it back in our d equation, and here's where we're looking at this is not distance, this is our second derivative formula, which is the second partial with respect to x twice evaluated at xy, the second partial with respect to y twice evaluated at xy, minus the second partial first with respect to x, then with respect to y, and then that quantity squared. So let's put our critical point into this formula, but we are going to need these second partials before we do that. So to get fxx, we're going to differentiate this with respect to x again, and that's going to give us 4. To get fyy, we differentiate this with respect to y again to get also 4. fxy, we differentiate this again, but this time with respect to y, and so we're going to get 2. So that gives us 4 times 4 minus 2 squared, which is 16 minus 4, which is 12, and that is greater than 0. Notice also our fxx was a positive number, and the second derivative test says that if d is greater than 0 and fxx is greater than 0, then we get a relative minimum at that critical point. So the domain element that minimizes this distance is 1, 0. That's going to make the z value also 0, and our ordered triple, where we get a minimum distance, is at the ordered triple 1, 0, 0. So this distance is the smallest possible. But the direction said to find the shortest distance, so now we're looking for the distance between 2, 1, negative 1 and 1, 0, 0. Now this d is for the distance formula, and the formula goes x coordinate minus x coordinate quantity squared plus y coordinate minus y coordinate quantity squared plus z coordinate minus z coordinate quantity squared, and this calculates out to be rad 3. So the shortest distance between our point and the plane is the square root of 3.